Dr. Bedekar, and distinguished audience, I am very much honored to be a chairperson of this last session. I am especially happy to tell you that all the three speakers now, Drs. Setsuro Ikeyama, Kim Profkel, and Clemency Montel, got PhD at Brown University under the guidance of Professor David Pingree. Another participant from Japan, Dr. Takanori Kusuba, and I myself were also Pingree's students. By the way, Professor S.R. Sharma, who played the great role in this conference, was invited to Brown University, and he was one of the examiners of Dr. Kusuba's PhD dissertation. So we 6 people are Brown affiliates. But we miss one important person, probably you know. That is, of course, Professor Takao Hayashi. I and Professor Sharma asked for Hayashi's participation, but he declined. He wanted to stay home and concentrate on his work. Everyone should know Hayashi's great achievement. As one of the evidence, I brought his book on the Bija-Ganita, which was published in the international journal called Skiamos, of which I have been the chief editor. With this work, the study of Bija-Ganita should be based on this book. Further studies should be started from this monumental work of Dr. Hayashi. And I want to dedicate this book to this conference. But yesterday, I promised to Dr. Sita Sundaram to give it to the people from Chennai. So before Dr. Ram brings this to Chennai, please take a look at it later. I put it here. Now, let us begin our session. First speaker is Dr. Setsuro Ikeyama. He is going to speak on an application of the addition formula for Sine in Indian Astronomy. Dr. Ikeyama has been a long-time co-worker of mine. He's the youngest of our groups and very brilliant. And now we are working on Neelakanta's commentary on Aryabhatiya Gora Pada. So please, Ikeyama.
Thank you. Hello, everyone. And it's a great honor for me to speak by our guru, Brahma Acharya. So, respecting the manner of this conference, first of all, I recite the small verse from Japan. So, Japanese verse is very short, just 31 syllables. So, it not needs too much time. Okay. Yeah. And this one, not the decoration, the Japanese word. 雨の海に雲の波立ち月の船星の林にこぎかくるみゆ星の林にこぎかくるみゆNow I start my speech. What? Do I say it? The first part is the ocean or sky as an ocean, and the the cloud as a wave, and the moon as a ship goes through the forest of the stars, and we can see it, and sometimes it hides, maybe back to the cloud. Such kind of meaning. Yeah. So, but my speech is very technical and mathematical, so not so interesting. Okay. So the first person in India who Hayashi. Oh, wood. Yeah, wood. So, not a legendary professor. Okay. And yes, Brahmacharya is the first person who introduced Bhaskara900, who introduced the addition formula for sine in India. So his Siddhanta Shiromani, Jia Utopati part, the verses 21st to 23rd AV, he mentioned the formula. Today I don't show any Sanskrit source and its translation, so I show just formulas. But this one, or I can use this. This is the formula of the additional formula of sine, and virtually it's the same as the modern one. But in Indian astronomy or mathematics, they don't use the common our sign, modern sign, but the so-called R sign. I show you the example of R signs, the tourage. So here is the angle kappa, and the bigger circle, this ZVP, is with radius r. So the arc ZV is here, and it's R sign. And I denote it in this notation. The first letter S is capital. So this means the R sign, and the R sign of arc ZV is BV. This is the relation of the large sign ZV and R sign, but this is the modern form, and the line BB. And also the cosine ZV, the large C, is the R cosine kappa, and this is the OB in this figure. This line, OB. This is the R cosine or cosine ZV. Okay, it's just a preparation of the discussion. So the additional formula can be written in this form using the name of this figure, and you will see this figure again and again afterwards. But Bhaskara900 did not give any demonstration of his formula, and his followers give the many kind of demonstrations. And this is one by so-called Kerala school or Madhava schools. It's a very basic one, and but so I have no good no enough time, so I skipped here. So please trust the Bhaskara900. This formula is correct, and I go further away. So today's story is the application of the addition formula for sine by also the Madhava. And the following discussion appears all in NAB4. It means the Aryabhatiya Bhasha composed by Nilakanta on the Gola Adhyaya. It's published here. I show you the published text. Is one. And the relating part is here. Yeah, and here is the Madhava's application form. But I can't read this one today. Yeah. Yes, this is the Madhava application formula. And for what purpose this application formula is used is to add the two arcs which is not on the same circle. So, and this is also the astronomical application. So this is a celestial sphere, and this line, this is equator, and this is ecliptic. And what we want to is the declination of point P. This is a planet. Declination means the distance from the equator. So the declination of P is that this arc A prime P. We need this arc. But the given is the declination of point V, where the P, the perpendicular from the P is touched to the ecliptic. And we have the declination of this point, V, and the arc AV. And also we have the latitude of the planet P. It is a VP. But these two arcs, AV and VP, is not on the same circle. So we cannot use the additional formula directly to these two arcs. So Madhava uses in these cases this formula for addition such. Figure, you need figure? Okay. How about this? Okay. Point A, yeah. Yeah. Point B. Oh, so this is at the not the case, sorry. it's the terrestrial equator. So. Lanka, yes, Lanka. At Lanka, so the prime vertical and the equator is coincident. Yeah. Sorry, I must say that one. Anyway, so Nilakanta limited the situation as a Lanka, not all over the world. So I try to explain how this application formula is found. And a very good explanation is already given by Professor Rama Subramanian and Rama Sriram, yeah, using the spherical trigonometry. But I now introduce the Nirakanta's way. He never used spherical astronomy. And so the following discussion is all in the NAV4, the Adiabatic version, especially after page 108. So maybe at 5. So so let's start explain the Nirakanta's way. So first, Nilakanta explained his own application formula in 3 steps. The first, he computed the BV from the given CV using this relationship. And BV is CV multiplied R over FD. Okay? So we get the line BV, this line, from the given CV. It's a very simple 2 triangles. This triangle, BVC plus C and ODF is similar. So this relation or Tarashka is used. Then once we found the VB, this figure is the kind of Chedeka. I don't know where this line ZVPD is here, this figure. So we now get the VV from CV, and we already have the latitude of the planet P, VP. So its sine, R sine, PU is calculatable. So the VP and PU is on the same circle. So we can use a normal additional formula and get the V prime P in this way. This is the same form of the formula. First I show here, this one. It's the same one. So now we get the B prime P. This is the R sine of arc ZP. ZP. And B prime P is here. So now we get the B prime P. But what we need is C prime P. So again, we must convert B prime P to C prime P. This is the third step. So the Nirakantar calculate the CP from using the B prime P and this Triashka. So also the same, use the same triangle. This one OFD, and this time is the B prime C prime P. These two is also the similar. So finally we get the C prime P, the declination of the planet P. And Nirakantar united these three steps into one formula. So this is it. The calculation is skipped there. Anyway, Nirakantar gets the C prime P in this form. No, in this form, the number 8. But the Madhav's formula is this. And please compare with these two formulas. This is the Nirakantar's, and this is the Madhava's. So the first term is the same, exactly the same. But the second term of the around here is cosine epsilon in the Madhava's formula. So the problem is how this OB times FD over R is equal to the cosine epsilon. And this is the main point of my speech, but no time is here. But I must say this form is correct. So Nirakantar is it's a very long story. So,そうですね。So anyway, finally, Nirakantar demonstrates that the part OB times FD over R, this is called the multiplier, but this is equal to the cosine epsilon. So the Madhava's formula is demonstrated by Nirakantar.
Okay, thank you very much. We know that Madhava is very great, and Nirakantar was as great as Madhava. So we are struggling with his Sanskrit text and carefully reading in this way. And so what he expressed in modern mathematics is just expression in modern way of Nirakantar's and Madhava's idea. This is what I want to say. We must be true to original Sanskrit text. Yeah. So, any question? Yes?
Yeah.
Yes.
This formula, of course, Yukti Bhasha has a different derivation, you know.
Oh.
Yeah, it is. Your Tattva mentioned only a few of the spherical trigonometry formula using Yukti Bhasha, and we did other things with modern spherical trigonometry. But Yukti Bhasha has a somewhat different derivation, you know,
So
somewhat similar, but not this.
Yes, interesting to compare. Yes,
this is more similar to Bhaskara's method, you know.
Yes.
That is, you know, he uses a series of declination type formula. So, intersecting circles. Yeah. So intersecting great circles, several things.
But
So Yukti
I
Bhasha
don't
also
know
you
well about the Yukti Bhasha.
Yeah.
It's very interesting for me,
Yeah,
so
yes.
I try to read Yukti Bhasha. Yeah.
And some other question? Yes, Kim?
Actually, I have a question that's I also have in written form, if you would find it easier to look at. So blue paper, yes. So the question is, it's a very interesting discussion of how you get true declination by combining two quantities that are not actually on the same circle, or producing another arc that reflects both those quantities. But of course, the traditional Siddhanta approach is simply to say that the combined declination is the latitude plus or minus the ecliptic declination, and allow the fact that they're on two different circles doesn't make much difference. Does Nilakanta criticize that standard approach, and if so, what does he say?
Yes, he criticized this, and he clearly mentioned these two arcs, like the declination and latitude, is not suitable to simply addition in the Aryabhatiya Bhashya. Yes.
What is your view? Can the sine formula be true for two arcs which are not in plane?
What he said?
No.
Yes,
the
yes,
addition
yes,
formula, can it be therefore assume that it is true for two arcs which are not in a plane? Specific configuration because of which the addition formula is going through, even when the two arcs are not in the same plane. Okay, we'll discuss it later.
Okay, please give me the detail. Sorry, I'm not a good English speaker. Is that it? Okay. 雨の海に雲の波立ち月の船星の林にこぎかくるみゆ That's all. 星の林 Yeah. This is a tanka. Haiku is more short. Yeah. Tanka means a short verse or short song. 31 syllables. 57577. And haiku is just the upper part. 575. Thank you very much.